Hello there, Mr. Sutton here, bringing you the BC Calculus 8.3 Extra Practice Number 4 solutions on vectors. On this one, I'm given the position of a particle with a set of parametric equations here. We want to know the velocity vector at time 1. So to get the velocity vector, I basically need x prime of t comma y prime of t. And to get that at time 1, I just need to plug in 1 for t. But since this is a no calculator problem, I need to actually figure out what x prime and y prime look like algebraically before I can plug anything into them. So let's start with x of t. This is going to be, if I take the derivative, 1 over t squared plus 1 times the inner tail of 2t. So there's the 1 over t squared plus 1, and now we have to multiply by the derivative of the inner function. So that's a 2t there. And now for the derivative of y prime, that's going to be negative e to the 3 minus t, using the chain rule there as well. Smaller chain rule, though. So this times negative 1. So now I'm going to plug in 1 for all this stuff. So I'm going to have 2 times 1 over 1 squared plus 1. And then, let's see, for this next one, I'm going to have, let's see, this will be a negative e to the 3 minus 1. Cleaning that up a little bit, this is really 2 over 2, which is just 1. And over here, this is just going to be negative e to the second power, which ends up giving me, let's see here, answer choice B. For this calculator-based problem, we have the position of a particle given by this x of t and y of t set of parametric equations. We want the speed of the particle at time 3. So for this, I basically need the square root of x prime of 3 squared plus y prime of 3 squared. So this setup right here. Now, the good news is, since this is a calculator problem, I don't actually need to figure out what x prime and y prime look like in terms of algebraic derivatives. Not that these would be that hard to find, just use the power rule. But I can actually just find these derivatives directly on my calculator. So let me do that now. So here I am in my y equals. To start the process, I've entered x of t as my y1, and y of t is my y2. Now let me quit out of there and do this whole square root dance. So I've got a square root, and in there I need to take the derivative of x at 3. So we do math 8 dx, and then I need the derivative of x, so that's going to be alpha trace y1. That's where I stored my x function. I need to take that derivative at 3, so x equals 3 there. And now I'm going to press the right arrow just to get out of that little sub box. And now I'm going to square that. So that gives me x prime of 3 squared. Not done though, I have to add y prime of 3 squared. So let me do math 8 again, dx, and now alpha trace y2, so that I'm taking the derivative of y. We're doing that at 3, just like we were doing for the x one. And right arrow, square it, and press enter now. That gives me 41.725, which is going to give me choice D. On this problem, I'm given g as the vector valued function defined as follows here, and they want to know what g prime of pi over 3 looks like. So I basically just need to take the derivatives of these two components and plug in pi over 3. So for g prime of t in general, I'm going to have, let's see, this is going to be negative 2 sine of t. And for this next one, this is going to be 4 cosine of t. So now let me just do g prime of pi over 3. Just plug pi over 3 into both of those. And if, let's see, if I'm taking the sine of pi over 3, that's like sine of 60. So that's going to be radical 3 over 2. And we still have this negative 2 that is hanging around. I'll simplify that in a minute. Cosine of pi over 3 is 1/2, so we have 4 times 1/2. Reducing this just to get one of my answer choices, these 2's can cancel, so that's negative radical 3 for the x component. And for the y component, 4 times 1/2 is just 2. So we have negative root 3 comma 2, which is choice C. For this one, the instantaneous rate of change of a vector-valued function f of t is given as this r of t function. So this is basically f prime of t. And they're telling us f of 2 is 2e comma pi minus 7, which is kind of weird, but these are just coordinates basically. We want the value of f of 6. So to get this, I'm going to have to use the fundamental theorem. Basically do initial value plus an integral of the rate of change over some interval. So to do that, let me first start by defining x and y separately. I'm going to call x prime e to the radical t, and I'm going to call y prime of t, this other one, this 10 cosine one, just so I can refer to them quickly in my work. And in fact, while I'm at it, since this is a calculator problem, let me go ahead and enter those in my calculator, because I know I'm going to need both of them. So here I am in my y equals. I'm defining x prime as my y1 in y equals, and y2 is going to be my y prime function here. So I'll be using those in just a moment. All right. At this point, to figure out the value of f of 6, I need to find x of 6 and y of 6 separately, since this is one of those parametric vector deals. So for x of 6, I need the initial value of x, which is 2e. This was the value when we did f of 2. So we have 2e plus, now I need to integrate the rate of change from 2 to 6 to get the total change in x from time 2 to time 6. So integral from 2 to 6 of x prime of t dt. Again, just using the fundamental theorem here. And let me go on the calculator to do that. So there was my y equals again. Let me quit out of this, and I'm going to do 2e, there we go, plus integral, so math 9, from 2 to 6. And I'm going to do x prime, which I stored as my y1, so I'll do alpha trace y1, and then dx, there we go. And that all comes out to 35.606. So if I have an answer where that's my x value, that's going to be my answer. It looks like actually there's only one answer with that for an x value, choice D. So I have a pretty good suspicion that choice D is the answer, but just for practice, let me find the y value as well. So y of 6, that's going to be the initial y value of pi minus 7 plus the integral from 2 to 6 of y prime of t dt. So pretty much same setup, but a different initial value, different function. Going back on the calculator for this, I'm going to yank my input from before. And instead of 2e for the initial value, now I need pi minus 7. So let me see, we got pi minus, and I'm going to have to do a little insert here. Insert 7, there we go. Still have an integral from 2 to 6, but now instead of y2, or y1 rather, I want y2. So alpha trace y2. Press enter on that. And yep, 5.283. So overall then, we have 35.606, comma 5.283, which confirms that we were looking for answer choice D. On this one, we have a vector valued function h defined as follows, and we want to know which of the following is h of prime of ln of 3. So we basically need to take the derivative of this thing, which, since it's a vector, means we need to take the derivative of the x and y components separately, and then we need to plug in ln of 3 to all of that. And since this is a non-calculator problem, I have to do all of this by hand. So taking my derivative of the x piece of this, that's going to be e to the t minus e to the negative t. So a little bit of a chain rule going on, multiplying by that -1 tail. And then for the next one, we've got e to the t, and this will be now minus minus, so plus e to the negative t. So careful with your sign changes with these e functions. Next, I'm going to plug in ln of 3. So I'm going to have e to the ln of 3 minus, this is going to be 1 over e to the ln of 3. And here we've got e to the ln of 3 plus 1 over e to the ln of 3. Now all of these e ln's are going to cancel out, giving us just a 3. So the x component here for h prime, this is going to be just 3 minus 1 over 3. And over here for the y prime, this is going to be 3 plus 1 over 3. Still got to simplify a little bit to get one of these answer choices. 3 minus a third, that's really like 9/3 minus a third. That's 8/3. And here we have 9/3 plus a third, so that's 10/3, giving us answer choice C. On this problem, we have a vector-valued function f of t given here, and we just want to find f prime of t, which basically means I just need to take the derivative of the x and y components separately and put it back together. So for the x piece of this, I'm going to need a chain rule. So I've got something to the third. That's going to be 3 times something squared, so 3 times t squared plus t, the whole thing squared. but now I have to multiply by the derivative of the something, derivative of t squared plus t. So that's going to be 2t plus 1 going in a parentheses next to that. And I'll do pretty much the same thing on this next one. So we're going to have 5 times t to the 4th plus t, all of that to the 4th power, times the derivative of the inner function, which is going to be parentheses 4t cubed plus 1. And now I just have to match that with an answer choice. Well, judging by the length, it's not going to be A or B. So let's see here. Down to C or D, we have a 3 out in front, and already the only thing that matches that is choice D. So yeah, it's looking like D has everything we need. For this problem, we have the velocity vector of a particle moving in the xy plane, given by dx over dt and dy over dt here. So they spelled out those derivative functions for us. And they also give us the initial position of the particle at time 0, which was 3 comma negative 5. So based off that, they want expressions for x of t and y of t. So if you look at all these answer choices, they're looking for some kind of integral sort of expression with a variable in the upper limit, and notice that the dummy variable inside each of these expressions is not going to match the upper limit variable. We have a different dummy variable, which that's how it's supposed to be. So let's start with the x here. So for both of these, we're going to use the fundamental theorem. We basically have the initial value plus the integral of the rate of change. So for x of t, that's going to be 3, the initial value of x, plus the integral from 0 to whatever time you want, so t in this case, of, and now we have to put the x prime in here, so that's going to be this t squared. But again, we can't use t because we already used that variable in the upper limit. We have to use a different variable for the dummy variable. So following the multiple choice answers here, we're going to use s. So this is going to be s squared ds. Now we're going to do the same thing for y of t. That's going to be the initial y value of negative 5 plus the integral from 0 to t of, and now we need to use dy over dt in there, which was initially e to the negative 2t. So we're going to call this e to the negative 2s ds. And we just have to match that with one of our answer choices. So it looks like, let's see here, that's going to be answer choice C. For this problem, for time greater than or equal to 0, we have a particle moving in the xy plane, position vector of x of t, y of t, and those are both given here. We want the acceleration vector at time 2. So basically, we need to figure out x double prime and y double prime of t and plug 2 into those. And I don't have a calculator for this one, so I'm going to have to do this all by hand. Let's start with x prime and y prime of t. So for x prime of t, we have t times e to the negative t that I need the derivative of. That's a product, so I'm going to have to use the product rule, u prime v plus uv prime. Let me set up my box and ribbon for that. So I have my u and v values, t and e to the negative t, and their derivatives, which are 1, and this is going to be a chain rule here, so negative e to the negative t. Multiplying that out with the ribbon, we've got e to the negative t minus t e to the negative t. So that's just the x prime there. For y prime, I've got the derivative of this stuff. So that's also going to require a little bit of a chain rule. I have, let's see, ln of something. Derivative of that is going to be 1 over the something, 1 over 2t plus 6, times the derivative of the something, so times 2. And I'm going to clean up this y prime here because I'm going to have to take another derivative in a sec. So this 2 can cancel out with the 2 and the 6 down here, giving us 1 over t plus 3. And I'm just going to rewrite that as t plus 3 to the negative 1 power, just to make it easy to take the derivative of this thing again. All right, time for another derivative to get a of t now. So this is going to be v prime we're doing. So x double prime, starting on the left, this is going to be negative e to the negative t. And now we have to take the derivative of negative t e to the negative t. That is another product rule. So we have a negative t and an e to the negative t. Derivatives are going to be negative 1 and negative e to the negative t. Using the ribbon to multiply that out, I've got negative e to the negative t plus t e to the negative t. So that was x double prime I just found, and I'm going to clean that up in just a sec. And then we have derivative of this stuff to get y double prime, So that's going to be negative t plus 3 to the negative 2. All right, so at this point, I'm going to plug in 2 for t, because I really wanted an acceleration at time 2. And I'm also going to clean this up as I do it. So these two negative e to the negative t's here, I'm going to call this negative 2e to the negative t, which in this case means negative 2e to the negative 2, because that's what I'm plugging in for t. And we also have a plus 2e to the negative 2 there. And then over here, I'm just going to rewrite this as negative 1 over 2 plus 3 quantity squared. Simplifying a bit, it looks like these two things are exactly the same term when you get down to it, just opposites. So we actually have an acceleration vector for the x part of this of 0. X double prime of 2 is just 0. Negative 0, how about just 0? There we go. That makes a little more sense. And then over here, let's see here. This is 5 squared, so 25 down there. So overall, negative 1 over 25 for y double prime of 2. And that's going to match answer choice B. For this non-calculator-based free response problem, for time 0 to 12, we have a roller coaster with position x comma y, and we have a velocity vector given right here. And we're also told that at time 0, the car is at position 0, comma 18. So our first task is to find the slope of the line tangent to the path of the car at time 2. So basically, we're trying to find dy over dx at time equals 2. To do that, using the parametric setup, we have to do y prime of 2 over x prime of 2. Well, y prime of 2 is just going to be 2 plugged into the y part of this velocity vector. So that's negative 2 sine of 2 pi over 4. And then for x prime of 2, well, if you plug 2 into the x part of this, it doesn't really matter what you plug in, you just get 10 back. So this is going to be, let's see here, sine of pi over 2, which is 1, times negative 2, all comes out to negative 2 over 10. And you could leave it like that or reduce it to negative 1/5. On this part of the problem, they want the speed of the car at time 6. So in general, then, we're going to need the square root of x prime of 6 squared plus y prime of 6 squared. Now, we actually have to plug in some numbers here for this. X prime of 6, well, x prime of everything is just 10, so that one's not so bad. For y prime of 6, we're basically plugging 6 into this function right here. So we have 10 squared plus, let's see here, this is going to be negative 6 sine of 6 pi over 4 squared. And this is actually all constants, so if you put some units on this, you could call this done. But if you wanted to simplify it a little bit more, we would first clean up this sine expression here. This is really sine of 3 pi over 2, which is going to be negative 1, times the negative 6 gives us a positive 6 that we're squaring after all that. And let's see there, this is 100 plus 36, so square root of 136. And this is speed, so the units on this is going to be meters per second. So radical 136 meters per second. And really, I mean, you didn't need to simplify even down to this, so I guess there's really no point in reducing the radical at all. Hey, let's just call this done. So thus far, this problem hasn't been so bad. It's been about a roller coaster, and there's been some ups and downs, but it's been mostly downhill. Well, this is kind of the, this is more like a marathon, and this is the heartbreak hill of this problem. Part C here, I left a whole bunch of space because we're going to need it. So during the time interval, 0 to 12, we want the maximum value of y of t. So when you're finding the maximum value of something, especially when you're not allowed to use a calculator, we often use the candidates test, and this is going to be one of those problems. So we're going to have to test out the endpoints, 0 and 12. We're also going to have to find some critical values, which isn't going to be so bad. It's going to be kind of annoying, but the part that's going to really give us problems on this one is actually calculating y of anything on this. Because in order to do y of anything, we're going to have to use fundamental theorem and integrate this velocity y component, and that's going to involve some advanced integration. But we'll get there when we get there. So first, let's find critical values. So we need to take our y prime here and set it equal to 0. So here's y prime, and this is going to equal 0 where? Well, certainly at time 0 because of this negative t equaling 0. But also wherever sine of pi t over 4 equals 0. So where does that happen? Well, sine of whatever is going to equal 0. The sine of an angle is going to equal 0 where the y value is 0. So that's going to happen at 0, but also it's going to happen really anywhere you're on the x-axis. So pi, 2 pi, 3 pi, and we could go on and on. But eventually we're just going to find values that are between 0 and 12, so we don't have to go on forever. So let's calculate some of these values here, because we've basically gotten rid of the sign by inverse signing both sides and coming up with a few values over here. We still need to solve for t, though. So we're going to divide by pi and multiply by 4. So this gives us back 0. And then we have, let's see here, this is going to be 4. 2 pi divided by pi is 2, times 4 is 8. This is going to be 3 times 4, which is 12. And there's no point in continuing because we're only allowed to use t values between 0 and 12, and we're already full up on that. So we were going to test 0 and 12 anyway because those are endpoints, so that isn't really so bad. But 4 and 8 give us 2 more values we're going to have to test out. These are 2 more candidates. So it's time to plug a bunch of things into y of t. So I'm going to first get a formula for y of t so I know what I'm doing with all these different values. Let me start with a general formula for y of t. So that's going to be my initial y value of 18 plus the integral from 0 to whatever time I want of, and now I need to put this velocity component in here, but I can't use t because I already used it in the upper limit of integration. So I'm going to use a dummy variable. I'll use k. So I'll call this negative k sine of pi times k over 4 dk. The problem is taking the antiderivative of this is a little bit of a pain. We've got a negative k times this stuff. Integration by substitution isn't really going to work on this one because the derivative of this does not have a k in it. And we certainly can't use partial fractions or any kind of simplifying. Really, the only thing that's going to work on this, when you think about it, is going to be integration by parts. All right, well, here we go. That means that we need to pick out, well, let me first write my general formula. And then I'll figure out what all the different parts have to be. So this is going to be 18 plus, and now my integration by parts definite integral formula. I'm going to have an evaluation bracket with uv in it, and this is going to have the limits of integration here, so 0 to t, minus an integral from 0 to t of v du. So this setup here. So now I have to figure out the u and the v value for all of these. And, well, actually, I have to figure out u and dv, and then I'll get du and v based off of that. So just a little bit of a reminder, when I'm picking my u value, I use the acronym LATE to help me prioritize which functions make better u values. So the A stands for algebraic, like this negative k here. T stands for trig, like this sine function. I would prefer to use the algebraic negative k for the u function. And my reasoning on this is just based off things that are easier to differentiate, make better u values, and things that are easier to integrate make better dv values, or things that at least don't get worse when you integrate them. So I'm going to let u be k. I'll just use positive k here. And you'll see why I did this in a minute, but I am allowed to pick which one of these factors the negative goes along with. So I'm just going to go with k. For dv, I'm going to let that one be negative sine of pi k over 4 dk. And now I'm going to find du, that's the derivative of k. That's just going to be 1 dk, or just simply dk. This will be du here. And now I have to figure out the value of v by taking the antiderivative of this stuff. So normally this would just be a positive cosine of whatever was inside, pi k over 4. But I have to divide by this inner derivative of pi over 4. So I'm really multiplying by 4 over pi. So then I have v equals 4 over pi cosine of pi k over 4. And now plugging all this in my box here, I'm going to have uv. So that's going to be, let's see here, 4k over pi times cosine of pi k over 4, something like that, evaluated from 0 to t. And now I have to subtract my integral, so that's going to be minus the integral of basically this stuff times 1, so basically just this v stuff here. And at this point, it's time to take this antiderivative and move everything into one big evaluation box from 0 to t. So antiderivative of this, well, this would normally be, let's see here, sine of pi k over 4, but Now we have to divide by this inner derivative of pi over 4, which means multiplying by 4 over pi. But there's already a 4 over pi out here. So this ends up being minus 16 over pi squared sine of pi k over 4. So that's all being evaluated from 0 to t. Now if I plug in t to all this stuff, nothing changes except that all my k's get replaced by t's. So if I do that, I've got the 18 from the beginning. I've got now 4 pi times t cosine of pi t over 4 minus 16 over pi squared sine of pi t over 4. And then I have to subtract all of this stuff with 0 plugged in. Now if I plug 0 in for this first one, we have a 0 for k. That's just going to zero out that whole term. And if I plug in a 0 right here, well, that gives me basically sine of 0, which also zeroes out the whole thing. So really what I've written here in blue, this is what you're going to be plugging stuff into when you plug things into y of t. This is the function down here. So that was a lot of work, but now we know exactly what we're doing, and we don't have to do integration by parts 4 different times. We just did it once for the general case. Okay, now it's time to plug in 0, 4, 8, and 12. We'll start with y of 0. Now this one isn't so bad because we actually know y of 0. At times 0, the y value is 18. And if you actually plug that into this formula, what happens is you zero out this first term and you zero out this other term. So yeah, you do get 18. Now we need y of 4. That's going to be the 18 here plus, well, let's see what happens if I plug in 4. Let me start inside the trig function and work my way out. So right here we've got 4 pi over 4, which is just pi. Cosine of pi is negative 1. So let's see here. We've got a negative 1 times a 4 times a 4 times over a pi. So this is negative 16 over pi right there. And then over here, if I plug in 4, well, now I've got essentially sine of pi, which is going to be just 0. So this whole second term gets zeroed out. So we just end up with 18 minus 16 over pi. Okay, well, that's not very pretty to look at, but we just have to compare it, and hopefully it'll be clear when we look at the other candidates. So next, let's look at y of 8. That's going to be 18 again. We always start with that 18. And now if I plug 8 into these things, well, now I've got cosine of, this is going to be 2 pi. 8 pi over 4 is 2 pi. And cosine of 2 pi is just 1. And we have an 8 being plugged in for this t as well. So 4 times 8 is 32 over pi times 1 changes nothing. So plus 32 over pi. Over here, this is going to be sine of 2 pi, which is just 0. So that whole second term again gets zeroed out. So this is looking pretty nice. And finally, y of 12. We're starting with, you guessed it, 18. And now let's see, this is going to be 3 pi because you're doing 12 pi over 4. Cosine of 3 pi, we're back to negative 1. And over here, this is going to be 4 times 12, which is 48, but we had a negative 1, so this is minus 48 over pi. And now we've got all the candidates have basically stated their position. It is time to pick the best candidate. We were looking for the max value here, just to be sure. So I think we can agree that if you're starting with 18 and then subtracting something, given that there are things where 18 is not subtracting things, the things where 18 is subtracting stuff, those are not going to be the max. So this minus 16 over pi, 18 minus that, can't be the max. Neither can this other one here. So really it's down to 18 and 18 plus 32 over pi. Well, I think we can also agree that if we have a choice between a number and the number plus another positive number, yeah, the second of those is going to be bigger, 18 plus 32 over pi. So this has got to be the max, and they were just asking for the max value, so we are done. For this last part of the problem, if you survived part C, all you had to do on this one, and this is a really good example of why you keep reading even if a problem is kind of daunting, all you have to do here is write but do not evaluate an expression giving the average speed of the car over the interval 0 to 2. So just average value setup, we're going to have 1 over the integral length, so that's 1 over 12 minus 0, times the integral from 0 to 12. So already you probably have some points if you got this in there. And now we're just going to put in the thing that we're trying to average. So we have to write an expression for speed in terms of stuff that we already have. Speed in general is going to be the square root of the sum of the squares of the derivatives. So basically square root of x prime of t squared plus y prime of t squared. And we also have a dt there because this is all with respect to time. Now the question is, can I get away with just writing this? Well, they gave us a position of x of t, y of t, and then they said that down here was the velocity vector. So they basically did define x prime and y prime. So yeah, this should be enough, and we are done.